I want to start by first making a simple observation. Generative models, be they image generators, text generators, audio generators, or video generators, learn how to do what they do from training data. But what piece of the training data did it learn from? If you gave me a sample that was created by a generative model, can I look at the training data and figure out which samples it had to learn from in order to make that thing that it made? Well, to assess this, what we can do is we can ask the counterfactual question. What would the model have done if that data wasn't there? What would it have generated instead? If it generated something that looks significantly different from what it actually generated when it had access to the full training data, then that suggests that the model actually learned something pretty important from that piece of data that's missing in the counterfactual scenario, in this alternative counterfactual scenario. So before I move further, I just want to clarify the terminology. The counterfactual sample is what is generated by a model that was trained on an incomplete version of this data set in this counterfactual, in this alternative scenario. We call the end product the counterfactual sample. This is in contrast to the factual sample, which was what was generated in the real world, where the model actually had access to the whole data set. Now, this is not just a thought experiment. We can actually evaluate this, right? All you have to do is to go back to your training set, take out that piece of data that's in question, and then train a whole new model on that, new incomplete data set. And then, because what generative models actually do is they take randomness and use that to turn that into a sample, we can take that same randomness that was used to generate the factual sample. We can use that on the new model that was trained on the incomplete data sets and use that to generate this counterfactual sample. Okay, so that tells you if a model learned from a piece of the training data, but that doesn't tell you the whole story, right? What you really need to do to learn the full story is to look at the entire counterfactual landscape, the sum total of all possible counterfactuals. So that's what I'm illustrating here. At the top, you see the factual scenario where the model was trained on the full data set and a piece of the training data, and it generates the factual sample. The bottom 9 panels illustrate the 9 different counterfactual scenarios that you can obtain, each of which is one where you remove a piece of the training data, you retrain the model, and then you use the same randomness to regenerate the 9 different counterfactual samples. These 9 counterfactual samples make up the counterfactual landscape. And that, in total, tells you a story about where the model learned to generate what it generated. Okay, so that's a cartoon. What does this look like in real life? What does this look like when you look at a real example? Well, here what we did was we trained a digit generator on about 400 different digits. And then we use that model to generate a couple of samples, which I show in the column that's labeled the factual samples. We then calculated the counterfactual samples, the entire counterfactual landscapes for each of these generated samples. And you can see those, I'm flipping through those in the column that's titled counterfactual samples. And I'm also showing these incomplete data sets that gave rise to these counterfactual samples. And you can see that there's a deleted piece of data that's sort of going through that counterfactual data set. And by looking at this, right, you can sort of see a story begin to emerge. The counterfactual samples, the ones that are trained, that came from these incomplete data sets, don't really change much from the factual sample, except for in very specific cases. That being when you delete a sample that looks very much like the generated sample. Right, so this sort of tells us that the model's not learning much from, is only really learning from one sample. It only cares about one sample when it generates, and this is sort of actually indicative of some plagiarism that's going on with the model. You see how, when I'm pausing at a digit that looks a lot like something that the model generated, it loses the ability to generate that digit in the counterfactual sample. So that's great. We can calculate these counterfactual samples. This lets us analyze what's going on. We're done here, right? Well, not exactly, because what I haven't told you yet is to compute that last figure, we actually had to train about 400 different models. And so that's an extremely computationally intensive computation. It was only tractable for us because we had 2 things going for us. One, we only had a training data set of 400 samples. This is very, very small in the context of modern generative models. And we were training models that generated handwritten digits. These are very simple models to train. Anything else, a model that generates faces, a model that generates landscapes, these are all much, much harder tasks, and these models are much harder to train. So how can we scale up? How can we compute counterfactual landscapes for these larger and larger samples? So the way we can do that is through ablation. Ablation allows us to circumvent retraining. And I do want to explain how this works, so I'm going to get a little technical for a moment here. What we're doing here is, instead of training one single model on the entire training set, what we do is we train these little parameter groups that are independently trained on different subsets of the training data sets. So I've shown this on this figure here. The little circles up there indicate the independently trained parameters, and I'm showing which parameters are trained on which pieces of the training data by linking them with a line. And as you can see, none of the independently trained parameters are trained on every single training data sets. And then you can combine these parameters into a single model, and that gives you a model that has effectively seen the entire training set. But now what you can do is you can delete parts of the training. You can delete these parameters, right? You can delete parts of these parameters. If you delete all the parameters that has seen a particular training sample, then when you combine those parameters, the parameters that haven't been deleted, you get a model that has effectively forgotten that it has seen that training sample. And so this lets us compute these counterfactuals again, because now we can go through this whole analysis of computing the counterfactual landscape again. And we show here that we effectively see the same thing going on, right? This is the same example of training on about 400 digits to make a model generate digits. But unlike the retraining-based example, we can actually scale up. Instead of needing to train hundreds of models, we only have these 16 parameter groups that we need to train here. So this really lets us scale up to these larger and more complex data sets. So let's do that. Let's scale up and see what happens. In the last 2 minutes of my talk, I want to show you what happens when we actually do scale up to these larger data set sizes. Well, on the top row, I'm showing samples that are generated from these more complex models that have larger training data sizes. The one on the left here has a training set size of about 1,000, the one in the middle, 50,000, and the one on the right, 160,000. And on the bottom, I'm showing images that I pulled from their counterfactual landscape. And what we see is, on the left over here, right, you get a lot of variation, a lot of richness within the counterfactual landscape. It fluctuates a lot. And as you move towards larger and larger training set sizes, this fluctuation collapses. It disappears. Like there's barely any fluctuation in the counterfactual landscape on the right over here. And so what's sort of happening is, the way I like to visualize this is, like, you have the factual sample here in the middle, and you have these counterfactuals dotted around it. And this landscape, as your training set size gets larger and larger, it begins to collapse in towards the factual sample in the middle here. And by the time you get to training set sizes that are 100,000, 200,000, 1 million, it basically just, the entire counterfactual landscape is contained in this tiny volume that surrounds the factual sample. And this is an effect that you can actually quantify. If you look at the plot over here, what we did is we trained a bunch of models. Each dot in the plot represents a model we trained. The x-coordinates gives you the training set size, the size of the training set that was used to train the model. And on the y-axis, we plot the counterfactual radius, which is a measure we define to measure the variability within the counterfactual landscapes of the samples generated by these models. As you can see, a very strong and very predictive negative relationship here. I'd also like to point out that this is not just because, like, we're taking out a single piece of training data out of a massive data set. This effect persists even when we take out whole chunks of the data set. In this example, I'm removing 1% of a data set at a time to compute these counterfactuals. And we can see this effect, this collapse of the counterfactual landscape as well. Again, on the left, lots of variation. On the right, barely any variation. So in conclusion, ablation is a powerful method that allows us to discover how generative models learn from data at scale. And using it, we can discover these important things, like the collapse of this counterfactual landscape at large scales. how there's a huge amount of exciting work that's left to do here. So if what I said interests you, if you're interested in working in this space, I would, feel free to reach out to me. I've thrown up my contact info up there, and I would, shoot me a message. I would love to chat. I've also left out a lot of details from this presentation, so if you would like to learn more, I've also thrown up a project website. You can follow the QR to read more about our work. And with that, I'm done. Thank you.